I believe that the existence of these patterns challenges the idea that the only structure in nature is randomness.
Math and Fractals, the language and patterns of reality. Welcome back to God is Digital. Today, we journey into the intricate and mesmerizing world of fractals and mathematics, exploring how these fundamental patterns and their mathematical underpinnings reveal the hidden order of our universe. Mathematics has often been called the universal language, a tool that allows us to describe and understand the underlying order of the universe. In the realm of physics, mathematics is indispensable, providing the framework for theories that explain the forces and particles governing our reality. Constants like pi, the natural base e, and the golden ratio phi are fundamental in describing patterns and shapes in nature. The constant e, approximately equal to 2.718, is the base of natural logarithms and is essential in the study of exponential growth and decay. The golden ratio, phi, approximately equal to 1.618, appears in various natural patterns and human-made structures. But today we focus on one of the most fascinating and visually captivating concepts in mathematics, fractals, the language of reality. Mathematics, fractals are complex patterns that are self-similar across different scales. This means that no matter how much you zoom in or out, the pattern remains consistent. They are generated by repeating a simple process over and over in an ongoing feedback loop and are described by mathematical formulas, often involving complex numbers. The Mandelbrot set, a famous example of a fractal, illustrates this beautifully. By iterating simple equations, we create a complex and infinitely detailed structure. This iterative process, where a simple equation is applied repeatedly, reveals the deep connection between mathematics and the natural world. The ubiquity of fractals in nature. Fractals are everywhere in nature. The jagged edges of coastlines, the ruggedness of mountain ranges, the branching patterns of rivers, and the formation of clouds all follow fractal geometry. These patterns are not just aesthetically pleasing, they reveal a deeper order in the apparent chaos of the natural world. A beautiful example of fractals in nature is the structure of snowflakes. Each snowflake forms a unique, intricate pattern through a fractal process. As water vapor condenses and freezes, it creates branching patterns that are self-similar across different scales. No two snowflakes are exactly alike, yet they all exhibit the same fundamental fractal geometry, highlighting the universal principles that govern their formation. Tree branches and roots exhibit fractal patterns as well. The way branches split off from the trunk and how roots spread through the soil follow self-similar patterns that optimize light capture and nutrient absorption. Fungal mycelium, the intricate network of fungal threads beneath the soil, also demonstrates fractal behavior. This fractal nature is also visible in the growth of bracket fungus on trees, where each shelf-like structure forms repeating patterns that mirror the larger fungal structure. Although often hidden from view, the mycelial network spreads out to cover vast areas, forming complex and efficient systems for nutrient exchange. Our own bodies are no exception to the prevalence of fractals. The nervous system, with its complex web of neurons branching out from the spinal cord and brain, follows fractal patterns. This fractal organization allows for efficient signal transmission throughout the body. The circulatory system, composed of branching blood vessels from the heart to the tiniest capillaries, also exhibits fractal geometry. While major arteries and veins are largely consistent across individuals, the smallest blood vessels, including capillaries, branch in ways influenced by genetic factors and local tissue needs. This variability ensures the efficient delivery of oxygen and nutrients to every part of the body and the removal of waste products. Blood vessels branch out similarly to rivers and streams, highlighting the fractal nature of this essential system. Fractals beyond structure, function, and behavior. Fractals are not limited to physical structures. They also manifest in patterns of behavior and function. For instance, the paths taken by foraging animals often follow fractal patterns, optimizing their search for food. Human heartbeats show fractal characteristics, indicating healthy physiological function. Even subatomic phenomena, like electron orbits, and astronomical phenomena, like planetary motion, exhibit fractal behavior. The probability patterns of electrons around an atom's nucleus display fractal-like distributions. Similarly, the orbits of planets and moons show self-similar patterns when observed over different timescales. These examples highlight how fractal behavior spans from the microscopic to the macroscopic, connecting the very small with the very large. Fractals in the cosmos. The cosmos itself is a grand display of fractal patterns. The distribution of galaxies and star clusters shows fractal-like distributions. The rings of Saturn and other gas giants exhibit patterns that can be described using fractal mathematics, revealing the deep connections between the cosmos and the mathematical principles that govern it. Fractals in technology and art. Fractals also play a crucial role in technology and art. In computer graphics, fractals are used to generate realistic landscapes and textures. Artists use fractal geometry to create visually stunning and intricate pieces of art. These applications demonstrate how fractals bridge the gap between science and creativity. Chaos theory and fractals. Fractals are closely linked to chaos theory, which studies the behavior of dynamic systems that are highly sensitive to initial conditions. This sensitivity is famously illustrated by the butterfly effect, a concept where a small change, like the flap of a butterfly's wings in Brazil, can set off a chain of events leading to a tornado in Texas. The butterfly effect exemplifies how minor variations in initial conditions can lead to vastly different outcomes. This is why predicting complex systems such as weather is so challenging. Even a slight difference in atmospheric conditions can dramatically alter the path or intensity of a hurricane. While the outcomes of these systems are highly unpredictable, the underlying rules are deterministic, governed by mathematical equations. This deterministic nature means that if we had perfect knowledge of initial conditions, we could theoretically predict the future states of these systems. However, due to the immense complexity and sensitivity, perfect prediction remains out of reach. This interplay between chaos and order reveals the deep structure of reality. Fractals emerge from this chaos, showing that what might appear random or chaotic on the surface is actually governed by underlying mathematical principles. This understanding bridges the gap between the seemingly unpredictable and the fundamentally ordered nature of the universe. The philosophical implications. The self-similar nature of fractals suggests that the universe may operate on similar principles at all scales, from the microscopic to the cosmic. Fractals offer a way to understand the interconnectedness of all things, emphasizing that patterns repeat throughout the natural world. This holistic understanding challenges us to see the universe as a unified, interconnected whole. The role of math in understanding fractals. Mathematics is essential in understanding fractals. Unlike traditional geometric shapes, fractals have non-integer dimensions, known as fractal dimensions, which help measure their complexity. The concept of self-similarity is crucial in understanding how fractals maintain their structure across different scales, revealing the underlying order in the chaos. Conclusion. Mathematics and fractals provide a powerful lens through which we can view and understand the complexity of the universe. By recognizing the fractal nature of reality and the mathematical language that describes it, we can appreciate the intricate patterns that connect everything from the smallest cells to the largest galaxies. Join us next time on God is Digital as we continue our journey to uncover the secrets of our universe. If you found this discussion intriguing, please like, share, and subscribe to God is Digital. Let's continue exploring the fascinating connections between science and philosophy together. Until then, remember the universe speaks in patterns, and by understanding them we get closer to comprehending the digital nature of our existence.